So let's solve some relevant numerical problems. A rectangular plane surface is 2 meter wide and 3 meter deep. It lies in vertical plane in water. Determine the total pressure and position of center of pressure on a plane surface when its upper edge is horizontal, and case A when it coincides with the water surface, and B when it is 2.5 meter below the free water surface. So the first step is to draw the figures. So the first case is when this rectangular strip, which is 2 meter wide and 3 meter deep, the upper edge, which is horizontal, it is in contact with the water surface. So we can locate the G point, the center of gravity, and P point, center of pressure. Here in this problem, these are taken from RK Bansal, and the derivation is also taken from RK Bansal, but I told you earlier that I have changed the symbols. I'm using H dash to represent the center of gravity from the water surface. So here H bar is basically H dash. You can use any of the symbol, whichever is comfortable to you, and H star is basically HP, which is distance of P point from the water surface. So let's write down the given data first. So H dash for rectangular shape, we know the center of gravity lies at d by 2 distance. So it is 3 by 2, which is 1.5 meter. The area for rectangle is 2 into 3, 6 meter square. And IG is the horizontal axis passing through the center of gravity. For that, it will be B, which is 2 meter, into D cube, which is 3 meter. So 2 into 3 cube over 12. You can make out the calculation, and rest is to substitute the values in the formula. We're already familiar with this formula. We have derived it. The force for a vertical surface is given as rho G A H dash. I'll call it H dash. And it is water, so rho will be 1000, and G is 9.81, area is 6, and H dash is 1.5. And the force will be in newtons. And to calculate the center of pressure, the formula is HP is IG over AH dash plus H dash. IG you have just computed, it is 4.5, and area is 6, and H dash is 1.5. Simply substitute those, and you will have HP, which is 2 meter. So HP is 2 meter, it is below the H dash, which was 1.5 meter. So moving on to the next part of the problem, which is when the upper edge, it is 2.5 meter below the water surface. So according to description, the diagram is drawn, and now the G point, the distance from the water surface will be H dash, and in this case the only change will be in the H dash value, which will be now 2.5 plus 3 by 2, which is 1.5. So 2.5 plus 1.5, it is 4 meter. The rest value, area of the strip, it remains same. Sorry, area of the rectangle, it remains same. 2 into 3, 6 meter. IG value, it also remains same. So simply the force will be 1000 into 9.81 into 6 into 4 in newtons, and HP, it can be computed using the same formula. Only change will be the H dash, which is now 4 meter. So now it come out to be 4.1875 meters. So the next numerical, which is to determine the total pressure on a circular plate of diameter 1.5 meter, which is placed vertically in water in such a way that the center of plate is 3.5 meter below the free surface of water. So you have to draw the figure yourself. A circular plate which has diameter 1.5 meter, it is placed in water, liquid is water, in such a way that the center of the plate, which is the center of gravity, it is at a distance of 3 meters below the free surface of water. So H dash, it is already given, it is 3 meter. Area for a circular plate, we know it is either pi r square or pi d4 over 4. So area can be computed over here. It come out to be 1.767 meter square, and H dash is 3 meter. So put these values in this formula and you'll have your answer in newtons. And H dash, for H dash we need Ig. Ig, you know, it is pi d 4 over 64. And put all the values in the formula and you'll have the location of center of pressure, which is 3.0468 meters. So third numerical, a circular opening 3 meter wide in a vertical side of a tank is closed by a disc of 3 meter. So basically we have a tank in which we have a 3 meter circular opening which is covered with a disc of same size, and that disc, it can rotate about a vertical diameter. So the disc can rotate about the vertical diameter when the head of water above the horizontal diameter is 4 meter. So the head of water, that means the height of water above the horizontal diameter. Horizontal diameter indicates that it is passing through the center of this disc, which is the centroid. So distance from this center, from this G point to the water surface, it is 4 meter. So the distance or the location of this G point from water surface is given. So basically H dash is given, which is 4 meter. So we have to calculate the force on the disc, this total pressure force on the disc, and the torque required to maintain the disc in equilibrium in the vertical position. So first of all, let's solve the first part of the problem to calculate the force on the disc. And we know the force is given by rho g a h dash. H dash is given 4 meter. Area can be computed by this formula written over here. And you can also compute the Ig using. So after substituting the values in the formula, 1000 into 9.81 into the area into H dash, which was 4, we can compute this force, and for the center of pressure using the formula as used earlier, you can compute its value. Now this was simple. The new thing is the second part, which is to determine the torque required to keep this plate in a vertical position in equilibrium. So as we know, this force F force will be acting on this plate normal to it, and this force is basically trying to overturn it, or you can say open it. This bottom part, it will lift it upward. There will be space given over here. It will tilt like this. So we have to give a force, or you can say a moment, which will keep it in vertical position, in the same position, which will not try to turn it. So one way is to apply a force which is equal in magnitude and opposite in direction, and acting at same distance as this force from the G point. So this will actually it could be in a form of a clip or anything which will keep it in position. So they have actually asked for us for the torque. So torque is moment force into lever arm. So the torque till this G point, because of this force, will be force into the lever arm, which will be HP minus H dash. Right, the distance between P and G is HP minus H dash. So from here you can calculate the force into 4.14 minus 4, which comes out to be 388.31 Newton meter. So this force into lever arm, this moment, this is actually in counterclockwise direction. Okay, as you can see, it is in counterclockwise direction. So in order to resist it, we need a force which is we need a torque which is opposite in direction, equal in magnitude but opposite in direction. So the torque required is of the same magnitude but applied in clockwise direction. So the next numerical, problem number 4, it states that you determine the total pressure and center of pressure on an isosceles triangular plate of base 4 meter and height 4 meter when it is immersed vertically in an oil of specific gravity 0.9. The base of the plate coincides with the free surface of oil. So first step is to draw this figure. A triangle which has base and height equal, which is 4 meter, and the base, it coincides with the free surface of oil, and we can locate the G point and P point. For this triangle, we know that the A dash, which is 4 by 3 meters from the base, so it will be 1.33 meters, and the area is half base into height, and IG, it is given as BD cube over 36, because we are finding about a horizontal axis passing through the G. So the parallel dimension, which is B, it is going to be it will have power 1, and perpendicular will have power 3. So BD cube over 36. So rest the formula is same. I believe now you can do it. Use this formula for force and for HP, and you will have your answer. So let's solve the fifth numerical. A tank contains water up to a height of 0.5 meter above the base. An immiscible liquid, the liquid that does not mix with the other, of specific gravity 0.8, is filled on the top of the water up to 1 meter height. So we have a container at the bottom of which we have a water layer for a 4.5 meter height, above which an oil of specific gravity 0.8 is placed for 1 meter height. So calculate the total pressure on the side of the tank and the position of center of pressure for one side of the tank, which is 2 meter wide. So perpendicular dimension of this side of the tank is 2 meter. So this numerical, this has to be solved using a pressure distribution diagram. This cannot be done by the formula which we have just computed for vertical surface immersed in liquid, because that formula uses a constant density value throughout the submerged surface. So here in this case, where we have two surfaces, two liquids, so we need to consider the pressure distribution diagram. So we are considering the density of this liquid ρ1 for height h1, and density of water is referred as ρ2 for the height h2. So we know for the pressure distribution, we will start from the liquid surface, and it will be 0, and it will increase linearly, and at the interface this pressure is given as P1, this pressure, it will act as a surcharge load for the water layer, so it will remain constant, and this pressure is referred to P2, and the water layer will also exert pressure on the side of the tank, and that pressure is a triangular distribution with P3 as the base. Now this P1 pressure, this is ρ1, the density of the liquid layer, into G into H1, and P2 pressure, this is equal to P1, and P3 is ρ2 G H2. Now in order to calculate the force, we have to use the area under the pressure distribution diagram. So F1 is basically the base P1 into the height, which is H1 divided by 2. So we have the area of the triangle, so multiply it by the B, the width of the triangle, the perpendicular dimension, the width of this surface, the side of the tank. So F2 is P2 H2, because it is a rectangle now, into B, and F3 is a triangle, so P3 H2 into B divided by 2. So here it is given that the width is 2 meter. So B you have to take equal to 2 meter, not 1 meter. It is mistakenly written over here. So I believe now you can do it once you have all the information, and once you're clear about the pressure distribution diagram, then it's very simple. So after finding out these individual forces F1, M2, F2 and F3, you can compute the resultant pressure F, which is summation of all these three forces, since they are acting at the same direction on the same wall. So now it has come out to be 18148.5 Newton. Now in order to calculate the center of pressure, we have to take moment of all the forces about one point. It could either be about the base or it could be at the water surface. So here we are taking moment about point A, that is the water surface, or you can say, sorry, liquid surface. So the resultant force into its star, that is its center of pressure, is equal to the each force into its center of pressure. So we know this F1 force, this will be acting at 2 by 3 of the height AD, which is 1 meter. So F1 into 2 by 3 AD, because we know the centroid of triangle position is at a distance 2 by 3 d from the vertex. Then plus F2, and F2 will be its lever arm will be the AD dimension, which is 1 meter, plus 0.5 by 2. So 1 plus 0.5 by 2. So plus F3 into its lever arm, which is AD, which is 1 meter, 1 plus 2 by 3 into 0.5. 2 by 3 is now, so 2 by 3 into 0.5. So solve this expression for this HP for the resultant force, which will be 1.009 meter from top. So it is very important to write the reference point as well. You could also find out from the base, but since while derivation we have defined H dash and HP from the liquid surface, from the free surface, so that's why they've taken the same reference. So moving on to the sixth numerical. A vertical slice gate is used to cover an opening in a dam. The opening is 2 meter wide and 1.2 meter high. On the upstream side of the gate, the liquid of specific gravity 1.45 lies up to a height of 1.5 meter above the top of the gate, whereas on the downstream side, the liquid is available up to a height touching the top of the gate. So the first step should be to draw this figure using the information given in the statement. So we have to find out the resultant force acting on the gate and the position of center of pressure. Also find the force acting horizontally at the top of the gate, which is capable of opening it. Assume that the gate is hinged at the bottom. So let's see the figure first, in which we have this gate, which is 1.2 meter high, which is hinged at the bottom, and it is resting on the wall of a dam. And it was given a statement that in the upstream side we have a liquid of specific gravity 1.45, and this liquid is 1.5 meter high above the top of the gate. So this is a liquid surface, and above the top of the gate it is 1.5 meter high. On the downstream side we have water which is touching the top of the gate, and this is the remaining wall of the dam. And this is downstream side. Downstream is basically the lower end, in the direction of flow. The lower end, the lower part is called downstream. So in this numerical, basically this liquid of 1.45 specific gravity, it is exerting a force which is normal to this surface in this direction, while the water is exerting the force in the opposite direction. So we have to compute the resultant force on this gate. I believe you can calculate the force F1 and F2 very easily. The density of this liquid is given, specific gravity 1.45, so density will be 1450 into 9.81 into area of this gate, which is 2.4 into the lever, the distance till the center of gravity, which is 1.5 plus 0.6, so 2.1. So I believe this F1 will be calculated. Now let's see the F2 expression. F2 will be the water, so 1000 into 9.81 into the area, 2.4 into 1.2 by 2, so 0.6. Now, since these two forces are opposite in direction, so resultant force will be in the direction of force which is greater in magnitude. So since F1 is greater in magnitude as compared to F2, so resultant force will be F1 minus F2. And it came out to positive, that means our assumption that it is in the direction of F1, it's right. So I can draw my force F1 as well. So I can draw my force F, the resultant force, which is F1 minus F2. So it is in direction of F1. Now let's see the position of center of pressure. I could use a formula. I think it is better to use a formula for this liquid surface, since that pressure distribution formula, that is only valid when we do not have a liquid above the top of the surface. If we have such case, then that formula is no more, the pressure distribution is not valid. For example, if you are using pressure distribution, it would go like this. It would go like this. Let me rearrange it. The pressure distribution will be like this. And we do not have a surface over here at which we want to find this load, so the pressure distribution is no more valid. We need to use the formula. So HP, H1 P, or you can call HP1. It's easier to, if you're using the symbol HP, so it is HP1 or H1 star. You can use any symbol. Sorry for confusing this up with the symbols, but I hope that you will be able to simplify it. You can make your notes and then use single symbol in that. So this is IG over AH dash plus H dash. IG is BH cube over 12, where B is 2 and D is 1.2 cube. So this IG is here, and we can put all the values. We had calculated the H dash, which was 2.1 for the first case, so we can have this HP1, which is 2.1571 meters. And we can also calculate the HP2. HP2 is simple. This is simple, that pressure distribution, you know, it is going to be triangular, so it is acting at 2 by 3H, so 2 by 3 of 1.2. This is very simple. They are using the formula as well, but if simply you use it, 2 by 3 of 1.2, I think you will get the same answer. So this answer should be 0.8 meters. So now basically we need one common reference, because for HP1 it is its liquid surface, for HP2 it is water surface, so it is confusing. So we need to have one reference. So what we're going to do is we're going to use the hinge as the reference. So HP1 will be 1.5 plus 1.2, which is 2.7 meters, minus HP1. I can call that distance, I think, distance of the F2 from hinge, and they're not using any symbol. I can use Y with it. So this Y, which is the distance from the hinge, it is YP1 is 2.7 minus HP1 and similarly YP2 will be 1.2 minus 0.8. So it will be 0.4 meters. So now in order to find the location of the resultant force from the hinge, I will have to take a moment about that hinge. So the resultant force into its lever arm, I will have to write over here, the resultant force F into its lever arm HP is equal to the force F1 into its lever arm. I'll assume that this F into HP, this is producing a since it is acting in the direction of F1, so it is producing a clockwise moment, and I'm taking clockwise as positive. So this is equal to F1 into its YP1, and since F2 is in opposite direction, so minus F2, this is F2 into YP2, which is 0.4. So they are basically taking this F to the denominator, so we can have this HP, and solving it, we have our answer, which is 0.578 meter from the hinge. So I believe now this will be clear to you guys. So second part of this numerical was to find out the force which is acting at the top of the gate, which is capable of opening it. So this force, this is acting on the top of the gate, this is the F force, and we are basically going to calculate its moment about the hinge. So force F into its lever arm, which is 1.2, plus F2 into its lever arm 0.4, this is equal to F1 into its lever arm, which is 0.5429. So rearranging this expression, we have to rearrange the expression and calculate the force F, which came out to be 27725.5 Newton. Now a common mistake could be that you want to consider the resultant force in this expression as well. Remember, the force or moment due to the resultant is equal to the moment due to the components F1, F2. So you need to consider one, either consider resultant force or consider this external force, extra F force acting. You cannot take both. I mean, you cannot take F1, F2 as well as the resultant force. Either take these F1, F2 or take the resultant force, and then develop the equation to compute this capital F force which is acting on the top of the gate in order to open it. So the last numerical for today, a tank width is 2 meter and it is full of water. Find the total pressure on the bottom of the tank, the weight of the tank, and hydrostatic paradox. Alright, so going with the part A, the total pressure at the bottom of the tank. We know the pressure at the bottom is given as rho GH, and to calculate the force we have to multiply it by the base area. So it is given that the width, the perpendicular dimension of this tank is 2 meter. So area will be 4 into 2, and height is 3 plus 0.6, 3.6. So you will have your answer over here, which is 282528 newtons. Then the weight of the tank, you know, weight is specific weight into volume. So specific weight is 9810 and the volume will be 4 into 0.6 plus 3 into 0.4 bracket into the width, which is 2 meter. This 3 is the distance till this liquid surface. And the hydrostatic paradox, it is observed that the total weight of the tank, total weight of the water in the tank is much less than the total pressure at the bottom of the tank. This is known as hydrostatic paradox. So I think this will be cleared to you guys. And still, if there is anything, we can discuss it in our online session. So thank you. Allah Hafiz.